Hey everybody, so today I just want to talk a little more about proof by contrapositive. And this example, which is just right out of the book, is a really good example of a place where I would think to use contrapositive proof. So the reason is, if you're trying to do this directly, you would have to assume this whole big messy thing is true and use it to show this, which I'm sure you can do, but if you flip this around and negate, it's much easier to just assume this is not true and show that this is not true. And so sometimes if you get a problem this year where, what you're trying to show in our linear algebra class is really complicated in the front, but not so complicated at the end, maybe try to flip it. So assume this not true and show this is not true. Or you could try a proof by contradiction, which is what we'll talk about next time, but more on that later. So just to remind you too, this is why this method works. So if you just fill out the truth table, your original conditional has the exact same truth value as the contrapositive. So if you prove this case, if you prove this conditional, then it will work and for this too, they're the same thing. So whatever you prove here, if it's going to apply to this. So let's do that. So if I was doing a proof by contrapositive, to sound fancy, sometimes we might say, we proceed using a proof by contrapositive. And so we're going to assume y is not less than or equal to x, i.e. Y is greater than x, or y minus x is greater than 0. And then you could say something like, since x and y are in R, right? That's just given up here. We know x squared plus y squared is greater than 0. And so I'm going to say, therefore, if you do y minus x times x squared plus y squared, that should be greater than 0, right? It's just the idea if you multiply two positive numbers, it's positive. Now this is kind of maybe not clear where this is going yet, but if you just go and double distribute this thing out, okay, you could just say y, actually I want to say it different. I'm just going to say, therefore, yx squared plus y cubed minus x cubed minus xy squared is greater than 0, or equivalently, we have that yx squared plus y cubed is greater than x cubed plus xy squared. And then you could just say something like maybe since P implies Q is equivalent or logically equivalent to not Q implies not P, we have thus shown that x and y in R, that I'm going to say for x, y, and R, if y cubed plus yx squared is less than x cubed plus xy squared, then you have y is less than or equal to x. Done. QED. So, actually, let me say something else about this really quick too. I just thought. So, this step in here, this can sometimes be probably seem like when you read a proof that it comes out of nowhere, some of these sentences, but this is, when you have a part like x and y and R, that has to play a role. They're not going to just add that for no reason. So thinking about things like, oh, what makes something a real number is that you square it and it's positive, starts to maybe give you an idea that that's where you want to go. It could still be sometimes really hard, and this is the part that, like, you might have this short little sentence right here, and in writing it seems like it takes no time, but at home when you're writing up a problem set or working on a proof, sentences like that can sometimes take you like an hour or 2 hours just to figure out that that's like the best way to go next. A lot of times I feel like my thought process starts at the end and I like work my way backwards, and then when I write it up, I have to write it in this logically like flow. The logical flow needs to follow sometimes different from how I think about it, is what I'm trying to say. So don't just think that I just came up with this while I was talking. These kind of things you have to like spend time thinking about. This is just another example I thought was good out of the book, and I just wanted to kind of walk through it. It's, you can just read it too on your own, but there's like a few things that I think are good to see. So the thing I like is that it uses both proof by contrapositive and it uses cases. So all it says is that for two integers, x and y, if 5 doesn't divide x and y, x times y, then 5 doesn't divide x, and 5 doesn't divide y. It makes a lot of sense if you think about it. Like if you pick two numbers x and y, you can make up a few numerical examples that'll really sell you like, okay, that's definitely true. A lot of times there are going to be ways to do this direct and just go from here to here. But this is another one that's so much easier if you use contrapositive. So we're going to suppose that it's not true that 5 doesn't divide x and 5 doesn't divide y. And this is a place where we're going to have to use De Morgan's now, which is kind of nice. And that's part of the reason I want to show you this. De Morgan's is like the negate and flip. So the and is going to become or. So we're going to have that it's not true that 5 doesn't divide x, or that it's not true that 5 doesn't divide y, which is equivalent to just saying that 5 divides x or 5 divides y, okay? And there's basically just two kind of possibilities. You either have 5 divides x, and you would get x equals 5 times something, and then you could do, xy would look like 5a times y, and then they're just grouping the a and the y, and that's 5. This has then the structure of 5 divides xy. Like this is your thing in Z. That would be one case, right? That's this case here, the 5 divides x. 5 divides y, then you sort of just, flip some symbols around. Y equals 5a, let's say, for some a and z. And you can use the same a because they're actually not the same a, I guess, is the idea. Like this case, it's like a new whole set of things. Everything restarts. It's not like this a continues over to this case. These are totally disjointed cases. That's the idea of cases. So you're not going to like double dip here. But then it works basically the same. So xy equals x times 5a, regroup. Xa is your integer that satisfies the divides definition there. So 5 divides xy, and then blah, blah, blah. The above cases show that 5 divides xy. So it is not true that 5 doesn't divide xy. And that would be like a proof by contrapositive, because we started with the negative of this, and we showed the negative of this, so that original thing would be true. The last thing I want to just say, please read these 2 pages. They're really, really useful in the PDF that's online. They basically just cover a lot of do's and don'ts of proofwriting. And there is like a skill to this, and this is not a proofs writing course per se, but a lot of times students would have a proofs writing course by the time they take linear algebra. And, since we have the time, I want to make sure that you guys can get as good with this stuff as possible. And it's kind of a fun thing, I think, too, to learn this skill. It felt very new to me, and when I first learned it, I was very bad at it. And when I started just kind of, put my brain into it a little more and really thinking about the way I'm unpacking arguments and the order in which I bring my points to paper, I realized it's kind of fun. It feels like you're doing some sort of, you're like a lawyer or something in a courtroom, and you're like, trying to really sell your case on why something is true or not. There's a lot to it, and you could read many other textbooks that go even more in depth into what we're just doing here for a few days. But this will really help. I read through those pages. It just takes 10, 15 minutes or something, but I think you'll get a lot out of it. They do a nice job of showing you what's good and what's not good to do when you write proofs. And that's about all I want to say for today.